let's talk about a few organizational things. The first being, I'll go to the OWL, your final exam. So, actually, before we talk about the final, I want to talk about next week. So like I said, there is actually class next week. It is optional. Don't feel like you have to come. There's no lectures, but it will be a kind of review. So to pick what we're going to talk about, if there's anything you would like me to go over again, if you have specific questions you want covered during that session, there is a Google Doc that you should be able to edit so you can see what other people have said as well, so things don't repeat. If you're not comfortable filling out the Google Doc, you can send me a question and I can put it on the Google Doc. That's okay. But yeah, so that's what we'll do next week, as long as the doc has some stuff in it. If there's nothing in there, then I suppose we won't meet. I'll probably still come here if you guys have questions and want to talk to me, but you'll be able to see what we'll cover if you look in the document. Any questions about that? Pretty clear? Alright. It'll probably be a pretty small group of us, so it could be nice to kind of have a bit of one-on-one back and forth, and with a couple of your peers who are kind of have some questions, right? So I would recommend that if you have questions, you put them there. If you want to go over certain topics, you put them there, and then come to have a more, small discussion. Could be pretty nice. But I also understand that it's kind of strange that there's just one day next week where there's class. So if you don't want to come, don't sweat it. All right. The next thing is the final. So I'm going to have a document available for you guys to study from, just like we did for the other two tests. And I did write the final already, so that's done. We had to get them printed. So let me just pull it up on my computer here without putting it up here, because that would be a problem. But there's about I think there's about 24 multiple choice questions, I think, 24 multiple choice. Let's double check that. Yep, 24 multiple choice, and then the next part, you choose 3 of 6 to answer, just like the other two tests. And then at the end, there's going to be a required question, just like always. This one required question is out of 6 marks, okay? And this one is going to be based on the information we talk about today. So the required question is based on today's lecture material, okay? Any questions about the final exam? Okay, it's not cumulative. I think I've said that already. So it's only testing the material that has not yet been tested. And I'll have a document up on this tab, actually, probably, with a kind of study guide, learning objectives document. I'll have that up as soon as I can. Your test 2 scores, they will 100% be out before you write your final exam. Will they be out next week? We're doing our best. There's lots to do, but keep an eye out for that. I don't want to have them up any later than April 16th. So I know that's 2 days before your final, but that's my goal. So that should be graded. I also want to I basically want you guys to know your entire grade going into your final. So I'm hoping to also have the second assignments that are due tomorrow night up before your final exam as well. If getting your grade right before your final exam makes you nervous, don't look at your grade book. Okay, some people they're like, oh, why would you release them right before the exam? Like, well, some students want to know. If it makes you really upset to look at your grades, don't look at your grades yet. You can control that. Okay. Any questions about the assignment or about getting your grades back? No, you guys are good? Okay, no questions. Everyone just wants to go home. Okay, so we're going to talk about lecture now. So this is going to be a bit of a shorter one because we're kind of wrapping things up. Okay. So lecture 11, our last one. Also, thank you guys for being here. I mean, most of you come every single week, so it's nice to see all of your faces. I really appreciate it. It's been a really good class. Okay. That being said, complex cognition. So, what does that mean? Complex thinking, right? Cognition that has some kind of complex mechanism, some simple mechanism. Things like human language would be considered a complex cognitive task, right? Okay, but when we're talking about animal cognition, we've talked about lots of different kinds of cognition, aspects of cognition, I should say. And we've often tried to find kind of simpler explanations for a lot of these seemingly complex tasks, right? And that's kind of what the theme of today is going to be. That you can look at a lot of behaviors that look really complicated. They look like they're complex, but they're actually achieved by pretty simple mechanisms. They don't have to be achieved by anything too remarkable. They can be achieved by things that are pretty mundane. And we've talked about that a little bit already, that that's a bit of a killjoy sometimes. Okay? So that's kind of the theme of what we're talking about today. Okay. So the reading that you have for this week is not in the textbook, so we're done with that textbook. What you have instead is an assigned paper that's uploaded on the OWL that you can download. It's just a few pages, 5 pages. So that's going to be the reading for this week, and that should help you understand this material in a bit more depth. So that's called Clever Animals and Killjoy Explanations. That's the name of the article. And before we get into some of the main arguments for kind of simple mechanisms underlying complex behavior, I want to talk a bit about what a killjoy explanation actually is, right? I mentioned it a few times, but what is a killjoy explanation? So it's an explanation that focuses more mundane, more boring, simpler mechanisms to explain a seemingly complex or oftentimes human-like behavior. Okay. So that's a killjoy explanation. So that's a pretty important definition to know. Okay? That's kind of the theme of today. So you should know what a killjoy explanation is. So they're called that because they kill the joy. They dampen the need for complex mechanisms or more kind of romantic views of animal cognition. Okay. This kind of thinking about animal cognition was really pioneered by Sarah Shuttleworth. Okay? And she is in the psychology department at the University of Toronto. Here are some of her books that are quite influential and talk about these ideas. This is one of them here. This is actually the optional text for this class, so it's Fundamentals of Comparative Cognition. If you have this book, again, not required, but if you want to read more about this, the last chapter talks about this quite a bit. This is a really good book. Even if you didn't buy it and you're really interested in this topic, I would really recommend picking this up and giving it a read. It's pretty short, right? Okay. But some of her longer books are here. Cognition, Evolution, and Behavior talks about these topics in more depth. But yeah, she's a pretty big figure in the animal cognition world. Okay. All right. So you can break down a lot of Shuttleworth's arguments into 3 main points. Okay. And the first is that complex behavior, I mentioned this already, can have simple mechanisms. I think this is maybe one of the most important points that she makes. And here are the other 2. So human cognition Because we're often comparing animals to ourselves, right? Humans can also be kind of animal-like. We can look at how humans are animal-like, right? We are animals. But human cognition can be simple and without conscious awareness. So not everything that human beings do, not all of their cognitive states, not all of their behavior is always complex. It can be explained simply. So this idea, this point, the second point, is kind of thinking about the animal-like in the human, right, as opposed to the human-like in the animal. Right. And she also makes the point that the way forward in comparative cognition work, right, when you're comparing species with each other, comparative work, should look at the differences and similarities between humans and non-humans without any kind of agenda. So the thought here with the agenda would be, think back to those enculturation experiments with the chimps. We talked about those last week, where you raise a chimp as a human being. There was a bit of a need there, or an agenda, to be like, okay, these chimps are basically humans, we can still teach them language, even though they don't have the vocal cords to speak, they can still have these abilities. And really the agenda there was to try to prove a theory wrong, one of Noam Chomsky's theories wrong, right? Just looking at the similarities and differences between animals to try to understand things about our evolutionary past, understand the ecological niches that those animals were involved in. That's potentially more interesting, or Sarah would think that's more interesting. Okay, and each of these sub-points beneath each of these major points we're going to talk about their examples for each of these thoughts, okay? All right, so let's start with the first one. Complex behavior can have simple mechanisms. I think maybe my favorite. Okay, Sarah, in the paper that you're required to read, I think it's in that paper, she talks about how there's a lot of times we can look at a complex kind of output from an animal and realize it comes from a simple mechanism without having to work too hard thinking about it. So, for example, termites. They make these huge mounds, right, that actually have a very sophisticated cooling system, which you can see here in the cross-section. But it doesn't take too much to convince someone, or it might even be kind of an intuitive understanding, that yeah, termites achieve this cooling system not because they have an inherent awareness of how cooling systems work, or that they have, they know about air conditioning, right? But they still build these really impressive homes that have these complex or these sophisticated cooling systems. So even though the cooling system is sophisticated, the termites don't need to know that it is, right? There's a simpler mechanism behind that. You can think of it like it's greater than the sum of its parts, right? It leads to something complex, but it started as a simple mechanism. Okay, but this isn't too hard to think, okay, yeah, of course. They're termites, right? They have simpler nervous systems than a lot of, than human beings, right? They have simpler nervous systems. It's easier to convince someone that insects don't have mental states, or probably don't have mental states compared to another animal, right? That in itself is a bit of scala natura fallacy. This is a bit of an aside, but just to let you guys know. There's this fallacy that comes up quite often when we're talking about animals, called scala natura, where there's a ladder. There's a ladder to life. Insects are at the bottom, then you have reptiles, then mammals, and human beings at the top. So there's higher and lower animals. That's a fallacy. Sarah does talk about that in the reading. Anyway, let's get back to this. Complex behaviors can have simple mechanisms. With the termite mound, kind of easy to understand. But let's take a seemingly complex cognitive trait and think about it from how could we get something complex like this from a simple mechanism. So we can use the example of insight. So in human problem solving, insight is likened to kind of an aha moment. A solution is suddenly perceived. And this is seen as kind of a complex problem solving phenomenon. But there is an ongoing debate when it comes to insight on whether this process really differs from trial and error, or a kind of type of analysis that just kind of adds simpler behaviors together. But we do know that experience with elements of the problem facilitate quicker solutions in humans and in non-humans, non-human animals. Okay, so these points will make a bit more sense when we go through the example. Alright, so first, we're going to talk about one of these classic experiments that's been used as an example of insight in chimps. You might have seen these before, or intelligence in apes. It's kind of a classic experiment where the ape pushes the box to climb up and then grab a banana, right? And these are actually videos from this experiment, so they're very old, right? So the thought here is that, okay, there's a treat out of reach for the chimps, and they're given these boxes, and they learn that they have to stack the boxes in order to climb on top of them and retrieve a treat, right? So this video is just very old quality, of course, but showing the chimps stacking the boxes to get higher up. We won't watch the whole thing, but that's basically what happens. One of those classic experiments in psychology. Kohler's chimps. But it was also done in pigeons. And so when this occurred in pigeons, it was a pretty big deal. So let's watch the video and see what the pigeon does. So it's trying to reach up to this object, which is supposed to be like the bananas hanging. And has a little box. It's got to move the box, right, to get the banana. So you can see, okay, I have to get up there. Somehow the pigeon knows, we'll talk about that it needs to get those bananas. This isn't actually a reward. Okay, seems kind of confused, keeps trying to go back. But staying on the ground, okay, realizes, okay, I can climb up on the box, yes. that didn't help. Okay, and then the little pigeon seems to realize what needs to be done next. Move the box. Oh, not quite. Okay. There you go. Very nice. Gets the bananas. Okay. So at first the pigeon seems kind of confused, right? But then some would argue, okay, but the pigeon has a moment of insight. It knows what it's supposed to do. It realizes, I have to move the box to get to the reward. So this has been shown as kind of this, okay, look, pigeons also have this complex cognition. They have this insight. Okay. So the pigeons, like I said, initially seem confused and then suddenly generate the complete solution. But how did the pigeon get that far, right? So in this experiment, there were several steps that the pigeon was trained on. They were all separate. So the pigeon had been in this condition before, wasn't trained on how to solve this condition, but had different conditions that it was trained on. So it was trained to climb and peck the banana for food, climb a box and peck at the banana, so the box would be in the correct position, so you would just have to climb up and peck the banana, get food. It was also trained to push the box, not to bananas, but to a dot for food. And it was also taught, do not jump at the banana. That's why, perhaps at the beginning, you'll remember the pigeon keeps going to the banana but doesn't actually jump. Right? And the pigeon certainly could do that and reach the banana. Right? But it was trained on all these little parts, right? Climb and peck banana for food. Push a box to a dot for food. Don't jump. And it was just trained, with rewards, associative learning kind of conditioning. Okay, associative processes. There's also this thought here that perhaps the pigeon makes this functional generalization during that condition there that we just watched. That banana is the same as a dot. Now this isn't too complicated actually. This is just explained by associative processes, right? This functional generalization, okay, associating those two stimuli together, again, making associations. And then something known as interconnection, so combining those behaviors in new ways. So behaviors that have been trained, which isn't too, that's pretty simple, right? We know that you can teach, there are lots of animals follow basic learning processes through conditioning. Like you can condition a snail to do something. You can condition a termite. You can condition an ant, right? So those are actually pretty simple mechanisms. It's just learning and then connecting those old behaviors in new ways. Yeah.
Were the chimps also trained?
Yeah, so if you go back and look, it doesn't explicitly say that, I don't think, in the original paper, but critics of that experiment have said, yeah, well, the chimps were trained kind of in a similar way to the pigeons. Yeah. Okay. Okay, so that's the first point we'll talk about. And you can think about this, like I said, think about how animals with simpler nervous systems can learn, right? Okay, so it's a simple mechanism, it works, right? Associating two stimuli together for a reward, that works. It's not that complicated. It's pretty simple. Okay. The next point that Shuttleworth makes, human cognition can also be simple without conscious awareness. And like I said, it's finding the animal-like in the human. You can also think about, we'll talk about one example, but a lot of implicit learning follows pretty basic processes, and we're not necessarily consciously aware of them. Okay. So this is a pretty interesting experiment where they had a sign above an honesty box for milk payments, so for coffee. So if you want to put milk in your coffee, you give some money to pay for the milk in this Department of Psychology. Okay? So what they did above the honesty box was sometimes they had a banner of flowers, above the box. And then they also had a banner with eyes. Okay. And this payment system had been going on for a long time. So they had the system for a long time, and then they added these images. And they wanted to see how much money do people pay when it feels like perhaps they're being watched versus a neutral stimulus. Kind of pleasant one. And the participants weren't told about the study. Okay. So people tend to be more honest or give more money when they are being watched, even though they're not actually being watched, right? So here are examples of the stimuli. Some of them are very scary, like this one's very scary. I don't know if they gave this guy like cat eyes or something. But what you can see is this pattern, right? So this is over different weeks. They kind of alternated them, right? 1, 2. People seem to realize after some time, perhaps, something about the eyes. I don't know. But on the first week, when they're shown eyes, they generally paid more money than when they just had flowers there. Okay. So the thought here is that, and people are, you know, they don't think someone's actually watching them, right? There's no, if you're in this situation, there's no mental state of, oh, I'm being watched, I should give more money, right? That's not happening. But it's some kind of unconscious process that actually has consequences. So human beings can be kind of like, I don't want to say dumb like this, but we're not always these complex, super intelligent beings all the time, right? We can give more money in a box when we think that there's just eyes looking at us. Okay, interesting. And, I think that's a fun example. So human cognition can be simple and without conscious awareness. Okay. All right. And then for this last point, I'm going to talk about an experiment. Again, it relates to the first 2 points as well, this last point. And so does this example. But looking at differences and similarities between humans and non-human animals without having, you know, an agenda. Okay. So here we're going to talk a bit about actually path integration in human beings. Okay. So path integration, if you guys don't remember, that's the process. We talked about it with the examples of the ants. We talked about desert ants, the experiment with the stilts and the stumps, right? But basically, path integration is a process which the relation of an animal to a location is updated as the animal moves. So the animal gets information while it's moving about where it is. Right? So they have to measure both direction and distance in path integration, right? And they calculate some kind of vector to go back home. Again, they're not actually calculating a vector, but that's what the behavior shows, right? So take a long winding path, have to get food, and then just go straight back. Because they've calculated information about direction and distance. Okay, so that's path integration. It's also seen as one of the most simple mechanisms of navigation, right? Okay. Doesn't require a cognitive map or anything like that. Okay. All right, so this experiment compared path integration in ants and in humans. Okay, cool. Ants and humans are pretty distantly related, right? One's an insect, and then we're mammals. Right? They wanted to see, okay, is there an actually similar process about navigation in ants in humans. Okay. So these particular ants, they don't use any visual cues. They don't use visual information. So what they did, because the ants they don't use visual information, these particular ants, what if we blindfold people? Don't give them any visual information. When you blindfold people, or you don't give them visual cues, humans use path integration. So what you're looking at in A, this is from that paper, this is basically a path of a winding path of an ant, and they take, in B, this is how direct their path is home. So different dogs, different ants, different trips, but it's kind of like the direction that they go in. So they take a vector, basically straight back. What you see in C, okay, so blindfolded participants were taken with an experimenter, and they were taken on this dotted path. So they go up, and they go down on two of these angles, right? And then they ask them, okay, find your way back to the start. And people actually they walk based on a vector. They take a more direct path back when they're blindfolded. Of course there are errors, they're not doing perfect, but humans can still use path integration. So we have this, finding the animal-like in the human, right? And it's a simple mechanism. Yeah?
Is that similar to how people who become blind, sometimes they do this type of physiotherapy where they learn echolocation, it's not quite the same thing?
So the echolocation in blind people, I haven't looked back at in a while, but it's not super common. But I would think, I haven't actually looked into path integration in people with visual acuity issues. I think the issue with that too is most blind people do have some vision. So even though they're not completely blind, they're still able, because they're not completely blind, they're still able to pick up on some information. Yeah. Or like my dad's actually blind.
Oh.
So he might path integrate more than someone who sees more visual cues. I'm not sure, but he still has some vision, so he can generally, see around in his environment. But that's an interesting question. So I would definitely urge you to look into that if there's a study with blind people and path integration. Yeah. Cool. All right. So when we think about navigation in humans, we do know that humans use kinds of cognitive maps, of course, and we also use maps through technology. We're not going through our everyday life only path integrating, right? But it is a system that's available to us. And we might use it in conjunction with our other elements of navigation. So of course we do use these more complex mechanisms sometimes, right? But we can also use the same mechanisms used by non-human animals, like path integration. I think that's pretty cool. Okay, so looking at all of these points again, each of these are just an example of how you can explain these points. There are several pieces of evidence that kind of substantiate this view of animal cognition. And while it is a perspective, it's certainly one that I ascribe to. Okay. So what I take from Shuttleworth, maybe it's seen as killjoy explanation at first, but when you think about it, I think the fact that you can break down a complex behavior and see that there's actually a pretty simple process revealed is arguably even more exciting. And I think it calls back to one of the last sentences in Darwin's Origin of the Species. In his last kind of paragraph, he says, there is grandeur in this view of life. And he says that there's grandeur in the view of life when we're thinking about evolution by natural selection. Because again, that seems actually like a pretty simple explanation to explain all of the diversity on the planet. Right? Lots of different living organisms, and he's saying they all had a common ancestor, and through selection pressures, we became different species. Right? And he says, even though this is simple and you can think of this as actually a killjoy explanation at the time, there is, in a sense, a grandeur in looking at life this way. Or a beauty. Right. So this is just something I wrote thinking about this. So the complexity and interconnectedness of life as revealed through evolution by natural selection is revealed in Darwin's Origin of Species. Right? That's what he talks about. But rather than diminishing the wonder of existence, the scientific explanation of life's diversity actually enhances our appreciation for the web of life on Earth. So that's how I feel. So even though it's seen as like a killjoy explanation, I don't think it actually kills the joy at all. I think it's pretty beautiful, actually. All right, I'm not going to cry here about animal cognition. All right. So final thoughts or questions for you guys to think on. Some of these points kind of have this undertone of being wary of anthropomorphism, right? Treating non-human animals as just little people. We all engage in it. We do it all the time. We talk about our pets. We talk about what they're thinking. It's automatic. And maybe there's no harm in it, really, in everyday life. But does it have a place in animal cognition research? I think a good example to think about this is when we're talking about animal intelligence. I always like to wonder, what is the definition of intelligence? It's even hard to define in human beings, right? Intelligence researchers will tell you it's difficult to define exactly what intelligence is. There's a debate about what it is. Again, colloquially, we all know what intelligence means. But from a research perspective, what's your operational definition? Right? So in animals, it poses even more of a challenge. What are you actually talking about when you're saying an animal is intelligent? Is the intelligent behavior just human-like behavior? So therefore it's intelligent? And is there another way to explain a behavior that seems intelligent? So if we go back and we think about the black-capped chickadees that are storing their food in various locations, and you have to remember all these different locations of food. That could seem like a highly intelligent task, right? If a person said they could hide thousands of objects and remember them all, we'd probably say, wow, that guy's pretty intelligent, right? But there's another way to explain that behavior, and it's that it's an adaptation that fits their ecological niche, right? So whenever someone says, oh, the animal is so intelligent, I always think about, are they saying it's human-like? That's the first thing I think. Or are they saying it's just a really good adaptation? Okay. And then some other questions. Should we be comfortable attributing complex cognition to animals through a kind of continuity of cognition? And the last point, sometimes there are special individuals within a species that seem to have really extraordinary abilities. So sometimes when we talk about experiments where, you know, 3 apes in this experiment could perform well. Are those individuals useful to the goals of animal cognition? I think they can be. I think that if you can show a species can potentially show a behavior, there's still value in that, or can show some kind of cognitive state, there's value in that, but they might not be the be-all, end-all, right? In understanding how, in most conditions, an animal tries to solve problems or an animal's cognition. Okay. All right. So that is it. Read the paper. Thank you so much for being part of the course. You guys were a great group. Okay. Thank you. That's very sweet.